In space exploration, man is an integral part of the spacecraft hardware. The human space traveler is able to serve a vital function which could not otherwise be performed. Man can make corrective control adjustments to compensate for certain electronic and mechanical malfunctions occurring within the space vehicle. But what is being done to protect man in this heretofore unknown environment? Bioastronautics personnel in the Air Force Systems Command are well qualified to select, train, conduct extensive research, and coordinate operational medical support in order to ensure man's safety in all manned space exploration. The resources are many, varied, and comprehensive, and are staffed by professionals of the highest scientific competence. Bioastronautics research activities span the continent. At Air Force installations and at universities and private industries sponsored by Air Force contract, professional staffs representing nearly every scientific area are teamed together with one objective: to support and sustain manned space flight. In order to illustrate the broad scope of Air Force bioastronautics research in support of manned space flights, many fundamental aspects of the overall program will be depicted. In addition, applied research associated with the factors involved at launch, during short-duration low orbital missions, during prolonged space travel, and at re-entry will be demonstrated. But before man is exposed to any facet of space exploration, instruments are sent aloft to gather information. Then biological specimens, including animals, are subjected to intensive biomedical space research. Some are launched in these piggyback containers. Many types of animals are used in the various stages of investigation, but chimpanzees are, for the most part, the optimum research animal for spaceflight because of their structural similarity to man and their aptitude for learning performance tasks. In the dry desert climate at Holloman Air Force Base, New Mexico, the Aeromedical Research Laboratory maintains a colony of over 50 primates for training and space environmental testing. In order to be utilized in space exploration, this intelligent animal must be oriented to unusual environmental conditions. Doctors of veterinary medicine, physiologists, electronics engineers, psychologists, and technicians give each chimpanzee childlike care in handling, feeding, and training. Comparative psychologists teach the animal complex performance tasks as part of this training phase. The pre-programmed tests teach the chimp to respond to a specific symbol displayed on the psychomotor display panel. A food pellet or a sip of water is the reward for correct performance. Environmental training, as well as all other phases of bioastronautics research, is under the constant supervision of highly specialized professionals. The chimpanzee precedes man in many phases of space exploration. New concepts of equipment must be tried and tested prior to placing man in the same environment. With this consideration in mind, Lockheed Missile and Space Company, Sunnyvale, California, working under Air Force contract, developed a primate capsule containing a closed environmental system, biomedical instrumentation, and a TV presentation monitoring system. Through successful application of data gained in the chimpanzee program and the concentrated efforts of the many interdisciplinary professions, life scientists are able to further their prime objective: the safety and functionality of the most complex of all missile subsystems, man. Prior to entry into the astronaut training program, the applicant must undergo rigid physiological and psychological acceptance examinations. Data collected in these tests by biomedical personnel are used not only in this evaluation, but are also stored for future reference baseline material. Initial baseline data acquisition is necessary for determining stress parameters or physical limits beyond which a human being could not safely proceed. After examining every aspect of the individual's clinical, physiological, and psychological state, the selectee is trained at the United States Air Force Aerospace Research Pilot School, Edwards Air Force Base, California. The astronaut must have adequate personal equipment which will offer protection during emergencies or when it may become necessary to leave the atmosphere of the capsule for any reason. At the Aerospace Medical Research Laboratories, Wright-Patterson Air Force Base, Ohio, special articles have been fabricated to test equipment. The final result is the creation of protective gear which far exceeds the human tolerance limits to severe external environments. Component parts such as wrist and elbow joints of full pressure suits are evaluated by anthropologists, physiologists, and by psychologists, assuring minimum detriment in human performance while guaranteeing maximum protection. Movement restrictions will be negligible and not hamper the astronaut so that he may instantly cope with any emergency situation. Simultaneous evaluations testing both man and equipment are conducted in many areas of this research and development. Reaction time to stimuli is tested on this computer program input and result analyzer. Personal comfort as well as safety must be examined in the many design and positioning experiments. With assurances of adequate protective clothing, we move now into other areas of continuous experimentation. At launch, there are 4 almost simultaneous occurrences for which the astronaut must have protection: noise, vibration, toxicity, and high forces of gravity. Toxicity data gathered during launch explore the potential hazards of noxious fumes and chemicals on both the astronaut and ground technicians. Records of noise and vibration at stage separation obtained in an actual space flight are used as test limits in laboratory investigations. These noise factors are reproduced in laboratory experiments. The ability to perform is studied during noise exposure tests. High-intensity noise exposure for even short periods of time can become physically intolerable to both support personnel and the astronaut. In addition, space operations require continuous, high-quality communications with the astronaut. Noise as an interfering factor must be reduced or eliminated. Vibration occurs during the high engine performance period at launch and prior to the time orbital velocity is achieved. These vibrations can become so severe as to lead to physical incapacitation. Research is conducted in biomedical laboratories to determine man's tolerance to this occurrence. In addition, training and familiarization programs are designed which tend to reduce the effects of vibration on the astronaut's performance. The effects of high G-forces incurred at time of launch and during successive ignitions of multi-stage booster engines have been thoroughly studied. Human tolerance limits in various body positioning experiments have been established on the centrifuge. Complementary Air Force-sponsored research conducted at universities across the nation leads to a supply of qualified scientists and to diversified methods of approach. Again, utilizing the most effective applications of our resources, both man and equipment are integrated into experimental high-performance aircraft. At the Air Force Flight Test Center, Edwards Air Force Base, California, testing under severe flight conditions is conducted in the X-15. Physiological instrumentation records the pilot's tolerance to the stresses incurred in flight. New miniaturized instruments located at strategic recording points on the pilot's body transmit information to a transistorized relay package situated behind the cockpit. This physiological data is then telemetered to ground stations and relayed to the Medical Control Center for instantaneous readout. Thus, both men and new miniaturized equipment are tested for performance under flight stress conditions. The second phase of spaceflight experimentation is concerned with low orbital space flights and research conducted in weightlessness. This state of zero gravity occurs when the velocity of the spacecraft counteracts the Earth's gravitational pull. Man and equipment must be able to operate in a weightless state. Training and testing procedures developed by Air Force human factors engineers who, calling on experience gathered over years of experimentation, are able to simulate some of the effects of zero gravity. At the School of Aerospace Medicine, Brooks Air Force Base, Texas, disorientation experiments are conducted in a 3-gimbaled chair, free-floating on a cushion of air. This apparatus provides 3-dimensional freedom, one of the conditions the astronaut will experience in weightlessness. Any space travel will result in long periods of confinement. Crew members must be able to withstand this psychological stress individually and as a working group. Biochemical changes which take place in man and in his environment must be examined. Changes occurring in space cabin atmospheric gases are also being investigated in a test cell inside one of the pressure chambers. At the Aeromedical Research Laboratories, men and equipment undergo simulated space cabin confinement for the detection of changes in these ambient gases. Adequate oxygen supplies are an absolute necessity to sustain human life. A sensing device developed by the Air Force detects an insufficient supply of this vital element on a moment-to-moment basis. As man lengthens the duration of orbital missions or ventures further into space, the logistic problems of providing a livable atmosphere manifest themselves to an even greater extent. Utilizing nature's own method of recycling carbon dioxide through plant life, the photosynthesis, or generation of oxygen, is produced using algae or other forms of rudimentary plant life. Another method of supplying oxygen includes the utilization of body waste to feed the algae or catalyze the photosynthetic reaction. In addition to its ability to produce oxygen and absorb CO2, algae are also being studied as a possible source of food or dietary supplement. Radiation in the Van Allen belts or from solar flares is under extensive study. Experiments using space-exposed bacteria, viruses, and tissue culture are conducted to determine the biological effect of radiation in various layers of the Van Allen belt. At Kirtland Air Force Base, New Mexico, development of a plastic man with the same atomic composition as human tissue enables scientists to accurately determine the depths of radiation penetration as well as doses without actual human exposure. Called the plastinaut, this fully instrumented subject is now undergoing tests in simulated radiation exercises. When the space traveler leaves his capsule for any reason, he will be subjected to temperature variations far in excess of those on Earth. Scientists from the University of Indiana and bioastronautics professionals are working side by side at the Wright-Patterson Climatic Chamber investigating this phase of research. Simultaneous extremes in temperature and humidity are simulated in order that various protective materials can be tested on volunteers to determine maximum safety and tolerance. In space, there will be no visual reference cues such as we have here on Earth. In early childhood, we learn to compare sizes of objects around us, and by doing this, we are able to estimate distances. Visual indoctrination tests train the astronaut to orient himself in the void of space. With no atmosphere acting as a filter, extremes in light will exist. Research into this field has led to the discovery of self-attenuating filters, which could have many other practical applications. Re-entry into the Earth's atmosphere poses another set of problems. The lessening of tolerance to re-entry forces from previous weightlessness is also being tested in simulated conditions. Severe buffeting will be encountered at the outer fringes of the atmosphere during re-entry. Maneuverability will be difficult in this situation. Biomedical research is attempting to increase man's ability to perform emergency functions during this critical period. Disorientation and forces of gravity will also be experienced during this phase of spaceflight. Rapid deceleration studies at Holloman Air Force Base determine man's tolerance to the forces encountered prior to or at impact. Methods are under investigation to reduce the severity of these forces on the re-entering astronaut. Instruments and protective devices are also put through a series of deceleration tests to ensure an adequate safety margin before incorporating man. Restraining couch tests determine the best methods of positioning a human subject exposed to landing impact. Escape is essential throughout the entire space mission. Tests being conducted in high-performance aircraft may prove to be the solution to this serious problem. Under investigation is a method of encasing man in a capsule, which would protect him in an emergency escape situation occurring within the Earth's atmosphere. Bioastronautics activities in the manned space program do not end at the research phase, but continue throughout the entire program, extending into the operational support of all biological and manned space flights. From a strategically located converted blockhouse used as the forward medical station at Cape Canaveral, medical monitors are in constant electronic contact with the astronaut or the primate during countdown, launch, and flight. Medical specialists also monitor the flight proceedings from the astronaut preparation area. This facility is on a standby basis and is prepared to render instantaneous major medical support for any occasion that may arise prior to or at the time of launch. The bioastronautics unit coordinates the emergency recovery force at the Cape. This recovery team, comprised of all branches of the armed forces, is stationed at strategic points near the launch site and is ready to spring into action if necessary. The advanced medical stations, such as the one at Grand Turk Island, are on a standby basis to render emergency medical assistance to the space traveler and as a facility for clinical examination of the astronaut following recovery in the planned impact area. This hospital and other similar facilities are easily relocated at various geographic sites along the programmed space track. Bioastronautic support activities circle the globe with medical personnel on ships at sea and at island-based advanced recovery hospitals. We have presented just a few representative fields of endeavor conducted through the supervision of the life scientists in the Air Force Systems Command. This activity requires the many technical disciplines of highly qualified specialists coordinating as a team with one objective: to effectively blend the intricate and complex subsystem, man, into the exacting high-performance spaceflight systems of tomorrow. Every aspect of research for the protection of man in the space program is being considered and investigated by the bioastronautics personnel of the United States Air Force.